Infinite series, part 6, part 3. So the last time we talked about the ratio test, but all the tests we did just had n in them. Now I'm going to do a couple examples with you where there's also an x. So you'll notice in this series there's an n cubed, there's a power of n, there's a 6 to the n, but there's also an x plus 5. So we're still going to be doing the limit as n approaches infinity. And so by the time we're done, the n will no longer be in our expression, but the x will be there. And this is where that whole, when we talk about the ratio test, it's the absolute value. That's going to come in the end, because we can see here, we have a series that's centered at -5. So I know my interval of convergence is going to be around -5. It's just a matter of what that radius is. And the ratio test is going to help us find that. Okay, so we're going to start with a pen. We're going to start with the limit. Seriously? Oh my God. Oh my goodness. There we go. Now we're cooking. All right, we're going to start with the limit as n approaches infinity of my n plus 1th term. So n plus 1 to the 3rd power. X plus 5 to the n plus 1 over 6 to the n plus 1 divided by my nth term. But instead of doing divided by my nth term, I'm just going to start off by doing an invert and multiply because it's less writing. So I'm just going to take my nth term, and the first time I write it, I'm going to write it as its reciprocal but being multiplied. Okay, so I can rewrite this in a way that's going to make it a lot easier to simplify. Again, some of you probably don't need to rewrite this because you're really good at visualing. I think I might be getting tired. Visualizing, but I'm not, so I like to write it all out. So I have a 6 to the n and a 6 to the n plus 1 that I know go together. I have an n plus 1 to the 3rd and an n to the 3rd that I know go together, and I have an x plus 5 to the n plus 1 and an x plus 5 to the n. Now once they're grouped like that, it's much easier to see what's going to happen. 6 to the n over 6 to the n plus 1 is going to become a 1 over 6. This is a cubic. This is an n cubed plus blah, blah, blah. This is an n cubed. That's going to go to 1. And I have an x plus 5. So I've got a 1/6 times an x plus 5, also known as x plus 5 over 6. Okay, so at this point, I'm evaluating my limit, right? It's all simplified. But you'll notice that in my limit, there is no longer an n. So that's like saying, what's the limit of 5 as x approaches 27? Well, it's still 5, right? So the fact that I'm taking a limit as n approaches infinity doesn't affect the value of this at all. So I still have an x plus 5 over 6 as my limit. And again, we don't really ever, people who are super fancy write it, but I never do because I can't stand absolute value signs in my way. Technically, this is an absolute value, and that really only becomes important in situations like this where we want to find an interval of convergence, because what we know is that the ratio test is going to give us convergence as long as the result is less than 1. In other words, as long as the absolute value of x plus 5 over 6 is less than 1. And that means that x plus 5 over 6 has to be between -1 and 1. And if we can solve this inequality, then we'll have an interval of convergence. So I have -6 over here. I have 6 over here. And when I subtract 5 from both sides, I end up with -11 is less than x is less than 1. So I have this interval of convergence that's between -11 and 1. And The center of that would be negative 5, right, which we knew from the start. So if it didn't come out to negative 5, we'd know we had a problem. And then you'll notice here, it goes 6 to one side, and it goes 6 to the other side. So depending on how the question is asked, we might be asked for a radius of convergence. If we're asked for the radius of convergence, our answer is 6. If we're asked for an interval of convergence, as of right now, our interval of convergence goes from negative 11 to 1. And notice that I have not included those endpoints. Okay? For now, we are not including endpoints. In the next recording, I'm going to show you another test. That test is going to allow us to look at those endpoints and decide if we should include them or not. But as of this moment, we cannot include them. Okay? And I will tell you why. Notice that these numbers, the negative 11 and the 1, are what is going to cause this to be either a 6 to the n or a negative 6 to the n. In other words, the 6 to the n is going to cancel out, and this will become a slightly different series at the endpoints. So we need a different test to look at it. Right, but for now, just leave them out. I always like to draw this picture here showing that they're left out, and then we're going to look at each endpoint individually and decide if we're going to color in that dot or not. But for now, we'll leave it out. Right, let's look at another example. Okay. This one is nx to the n over 10 to the n. So let's set up our good old ratio test. I have an n plus 1, x to the n plus 1 over 10 to the n plus 1. And I'm going to do my invert and multiply 10 to the n, x to the n. So if we separate out, we have an n plus 1 over n, which is clearly going to go to 1. We have an x to the n plus 1 over x to the n, and we have a 10 to the n over 10 to the n plus 1 if we separate everything out. That leaves me with an extra x on top and an extra 10 on the bottom. So an x over 10. And again, notice there's no n left. So when I do my limit as n approaches infinity, I just get x over 10, right? And what I need then is for the absolute value of x over 10 to be less than 1. In other words, x over 10 needs to be between, oh my goodness, between negative 1 and 1. Solve that, and you figure out that x has to be between negative 10 and 10. Again, look, negative 10 and 10, center of that is 0, and look, an x to the n. My series was centered at 0. In this case, I have a radius of convergence of 10, and my interval at the moment is negative 10 to 10. I will decide in a little bit if it is going to be, if I'm going to include those or not. Again, look what happens. When you put in 10 and negative 10, the series is going to simplify quite a bit. If I put in a positive 10, this is 10 to the 10 over 10 to the 10, and it just ends up being series n. Right, so we have to look at it a little more specifically at the endpoints. And we'll do that tomorrow, or the next time I record a video. All right. Okay, I want to go over one more with you, and this one is a little special for two reasons. The first is this little guy, n factorial. So I want to talk about how factorials simplify a little bit before we do this example. We know that n factorial, we know that factorial means to take the integer and keep multiplying by the lower integers until you get to 1. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1. And we know that 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And we did a little bit of simplifying with this when we did Taylor polynomials. Like if I have a 6 factorial divided by a 5 factorial, that simplifies to 6, right? Because this is 6 times 5 times 4 times 3 times 2 times 1, and this is 5 times 4 times 3 times 2 times 1. So you could really think of this as 6 times 5 factorial on top, and then a 5 factorial on the bottom, and those cancel. Well, we have to be able to do the same thing when it's in terms of n. So one of the ways to think about it is to think of n factorial as n times n minus 1, n minus 2, n minus 3, and so on and so on and so forth. Okay. So if I saw something like n plus 2 factorial, that would be n plus 2, n plus 1, n minus 1, n minus 2. It just keeps going down from there, right? But what I could do is I could say, oh, n plus 2 factorial. That's n plus 2 times n plus 1. And then this right here, that's n factorial. Okay. So if I had something like n plus 2 factorial over n factorial, I could say, okay, well, I'm going to rewrite n plus 2 factorial as n plus 2, n plus 1 times n factorial. In other words, instead of writing out n minus 1, n minus 2, because now I've got an n factorial in the denominator and I can cancel them. So in other words, every term from n down, there's an identical term in the basement of the fraction, in the denominator of the fraction that's going to cancel it. So all I'm left with on top is an n plus 2 and an n plus 1. So we're going to see that come up in the ratio test because anytime you have a factorial, here I have an n factorial. Well, guess what? When I write the n plus 1 term, I'm going to end up with an n plus 1 factorial. And we're going to end up grouping those together and needing to simplify them. But it's actually a really easy simplification if you understand the concept of factorials. So let's do this one, and we'll simplify that factorial when we get to it. All right, so I'm going to have a 2 to the n plus 1. I'm going to have an x to the n plus 1. And I'm going to have an n plus 1 factorial. And then I'm going to have over here n factorial, 2 to the n, x to the n. Okay, when we regroup, I have 2 to the n plus 1 over 2 to the n. I have x to the n plus 1 over x to the n. And I have n factorial over n plus 1 factorial. Okay, so if that was just an n and an n plus 1, we would say, oh, that goes to 1, or that's no problem. But that's not the case anymore. Right? So now when I simplify, I'm going to have a 2, I'm going to have an x, and this right here is going to be an n factorial on top. On the bottom, I have an n plus 1 multiplied by an n factorial. So my n factorials cancel, and I end up with a 1 over n plus 1. Now this is the first one of ratio tests where we have had an n left when it was time to take the limit. So now when we take the limit of this, the n approaching infinity doesn't affect the 2 or the x. It does, however, affect this. And as n approaches infinity, this piece is going to go to 0, which means that this whole thing is going to go to 0, which is a little shocking because now I don't have an x anymore. And I want you to remember what that means. 2 things. The ratio test says, as long as your result is less than 1, you have convergence. So the fact that we got a 0, just a 0, that's less than 1. Do we have convergence? And the answer is yes, we do. Right? And I want you to remember another rule that I always bring up in algebra. Whenever we learn to solve equations in algebra, like, oh my gosh, x plus 3 is equal to x plus 3. And then we go, oh, that's all real numbers, right? Because you end up with 0 equals 0 or 3 equals 3. And I always say to the kids, look, here's the deal. If a variable falls out of an equation, that's math's way of saying it doesn't matter, right? The variable doesn't matter. It's why when you have the equation for the volume of a cylinder, there's no variable for, the temperature in the room or the color of the cylinder, because those things don't affect its volume. Here, I have a limit where the x fell out. I don't have an expression for x anymore. That's math's way of telling us that the x doesn't matter at all. So the ratio test is saying, I have a value less than 1. That's convergence. And the fact that the x fell out is telling us it's going to converge. I don't care what x is. Doesn't matter what x is. And think about that. We've talked about a series like this before. What we really had in this series was 2x to the n over an n factorial. And if you remember, I don't remember what video it was in, we talked about how factorial grows so obnoxiously fast that it's going to shrink these terms like crazy every time. The fact that we got a 0 and our n dropped out tells us that our interval of convergence is just going to be negative infinity to infinity. It's great news. I don't have to worry about endpoints. If they ask for radius of convergence, our radius of convergence is going to be infinity. So I have a series here that is centered at 0, and it's going to converge everywhere. So I have a radius of convergence of infinity. Right? So if you are doing one where the x, you start with an x, but when you get to the end, the limit kind of, when you do the limit as you approach n, it kind of pushes the x out of the equation. If that happens, just pay attention to what your numerical answer is. If it's less than 1, that means your series is going to converge all the time. If it's greater than 1, that means your series is going to diverge regardless of what x is. Just like when there isn't an x in it. If the x falls out, it means the x didn't matter. All right, I'm going to leave you with that, and then we're going to do, I think, just one more video on the alternating series test, but we'll see how I feel. I feel like more than 15 or 20 minutes of me talking is too much talking. So we're just going to stop here for now, and then we'll talk about the alternating series test the next time we meet. See you later.